Hey, do we have a midterm tomorrow?
Yes, that's right.
No!
Well,
What time is it?
well, it says on our syllabus is from 1 to 5.
1
Okay.
to 5. That's that's
Well,
fine.
if you don't want that, if you don't want 1 to 5, we can change it. Or whatever it is, it will be 4 hours. Okay, 4 hours.
Oh my God.
Yeah, let me ask you. So if you don't like this time slot, if any of you don't like this time slot, just let me know. Okay, and we can vote for another time if you don't like it. Guys, any suggestion?
This is a lot.
Any comments or suggestion on the midterm tomorrow?
Hi, can we make it a little bit later?
Well, later would be greater for me because I don't have to wake up early.
So you can propose your time and we can vote for that.
Maybe 2 p.m. or something.
2 to 6, right?
Yeah.
So anybody who prefer 2 to 6, you can raise your hand and I can count.
Oh, wait, how do we raise our hand? Like that?
Well, that's okay, yeah. There is a reaction and or you can open the manage participant and there I think there are some options to raise your hand. Okay. Anybody who would like to make it 2 to 6 instead of 1 to 5?
Well, I think the question should be anybody who opposes 2 to 6.
So which means we have to. Well, it seems that Qitong
You have a
class end at 2 p.m. Okay.
So how about we make it 2:30 so she doesn't have to like run from a class to class?
We can change it like that. It's fine. So what
2:15.
change it to from 2:30 to 6:30?
That works fine for me.
So anybody who say yes, then you can make some, well, like send something on chat or raise your hand or just make something different, okay? If you would like to make it from 2:30 to 6:30. Okay. I only see 3, right? Yishui and well, and Aya and Wu Yue, and maybe Qitong. Okay, there are 4. There are 4 now. We need 2 more.
Most of them are just waiting sum up. Like most of them.
Okay. Zixiao. Okay, we need 1 more to make it majority. Okay, and then I think Yiwen also say that's okay, right? So we will change it to be from 2:30 to 6:30. Okay, 4 hours. And any other suggestion or comment on the midterm tomorrow?
Oh yeah, what would be covered on the midterm? Like, will we do
Well,
this?
it will cover everything we discussed, right? Everything we discussed on the chapter 1 of Strasbourg and chapter 1, 2, and 3 on Stan's book. Everything we discussed. If there are something we didn't discuss, like some very technical examples, then you can forget that. Okay, you don't need to assume. I will not assume you know that.
Okay, and then if I'll tell you that one exercise from homework I was doing for 2 hours, do you think that 4 hours, like, would the exercises in the exam would be like?
Well, it will not be. It will be, I think, it will be easier than your homework. Okay, it will be easier than your.
Okay, that sounds
Um,
better.
I have a question. Will there be any example questions?
Well, sorry about that. Well, I don't know what happens. I think it works now. I don't know why, but I hope it works now. I think it always like this. Well, for these times, for class, we got start and then we have to re-log in. Does it work now?
Yes.
Mm-hmm.
Okay. Where are we? So, mhm.
Will we have any example questions? Because I'm quite unsure for the exam tomorrow because I also spend a lot of time doing my homework.
Yeah, I know. But you guys, as I checked, you guys are all did your homework. Okay, at least did most of the questions. And I think the exam will be easier than your homework. Okay, so if you want to see examples, that's your homework. Okay, and based on what I can see from your homework, I think you don't need to worry too much about it. There will be no problems in the exams. Will be something like hopeless. Okay, it will be something solvable for you.
Okay, hope so. Thank you.
Yeah, I think so. Any other question? Or comments about our exams? Or any other thing? And well, it will be from 2:30 to 4:30. So I'll still have 2 hours. I'll still have 2 hours in the office hour tomorrow. And I think it should be from 11 to 1 o'clock. Okay. And well, from 11 to 1 tomorrow, I'll be here. And you can ask me any questions. And then well, our exam will start at 2:30 to 6:30. Okay, I hope it's clear. I'll be here in addition to my office hour. I'll be here not only from 11 to 12, but also from 12 to 1. Okay, tomorrow.
Oh, thanks a lot.
Okay. Any question?
Like considering homework or exams or just classes?
Well, first, for today's class, I will do one example on chapter 4. Okay, chapter 4 is really interesting. Stan's book, chapter 4 is really interesting. It provides you 3 examples, maybe I should say 4, but basically 3 examples about the application of Fourier series. I only tell you one, the simplest one, but it's also very amazing. I hope you will like it. And then, well, this example will not appear in your exam, and I will not assume you know this in your exam, but whatever, you'll see that it doesn't matter because it's really simple and really nice. And then I will try to do a short review, brief review on what we've learned on the first 3 weeks. And then I will try to go through some homework problems in your homework 2. Okay. Well, since you guys do have some problems on homework, and I said that probably I should provide you some solutions for you. But since next year I'm going to provide this course as well, so I probably have to recycle this homework problems. So it's better for me not to write it down. So I will just go through them on the class. Okay, I'll not write anything, so that you will not have the chance to give the homework solution to your classmate. Okay. But if there are some questions about the problems that I haven't covered, just let me know. Okay, I will just choose those problems such that most of you have some issues on these problems. So if you have any other questions about the homework problems, just let me know. Okay. Okay, so this is the plan for today. And by the way, so since it seems a bit hard for you to understand those kind of things, so we will change the schedule on our syllabus a little bit for our course. We will finish chapter 5 of our stance book. We will try to finish the chapter 5 of stance book instead of some other things on stress book. And we will postpone our stress book after we finish the chapter 5. Okay, after we finish the chapter 5, then we will try to do something on the stress book, like the green functions and green formula and so on. Okay, and maximum principle, comparison principle, and so on. Okay, but before that, we'll finish chapter 5 on the stance book. Okay, so before we move on, any question? Okay, so let's get started. First.
Oh wait, a little question. If we would go slower with this class, would we be behind in other universities?
Well, that depends. I think at least, well, for instance, for my university in China, at first, there's no standard schedule for this PDE course because it's kind of an advanced course. Okay, so there's no standard syllabus for this course. There's no standard contents that we should cover. And for instance, for the PDE course in my university, it was designed for those for the junior student, you know, for the third-year student. So it's different. So it's totally different from the PDE course of our university. And for some other universities of their PDE course, at least in China, they don't really like us, which cover a lot of things about the Fourier series. They only discuss the real PDE stuff, which is the wave equation and some properties of the wave equation and the heat equation, Laplace equation, and so on. Okay, so it will be different, but you don't need to worry too much about it, because first, there is no fixed content that we should cover. And second, well, as long as you could understand this course, well, the rest of this stuff, like something we didn't cover, but maybe Chinese university covered, this kind of content, you can totally understand them, for sure, okay? It will not be very hard, because for PDE course, as I said before, it should be an elective course, which means it's, well, if you don't really like it, you can even finish your degree without it, okay? I know a lot of friends of mine who are in grad school, but they don't really know anything about PDE. So that's totally fine. You don't need to worry about it. But of course, if you try to compare this kind of thing with Chinese university, then that would be a different story, because for Chinese university, they do have a lot of time, maybe more time to concentrate on this kind of stuff. So of course, they know more details about it. But if you are interested, again, if you are interested, of course, you can learn it by yourself, totally, okay? So which is why you don't need to worry too much about it. Okay.
Okay. Okay, thank you.
So let's see one more example about the application of Fourier series. Okay, this is not really a PDE example, and it's basically an analysis example. It just can show you why this well, Fourier series or the Fourier analysis is so powerful and is somehow very interesting. Okay. Basically, last time, or on chapter 3, or on the 3 lectures, we basically cover something about some very high level of structures of Fourier series. We try to understand the Fourier series in some sense like in linear algebra. Okay, we try to understand it that way. Here, we will try to see why we are so interested about the Fourier series. It's simply because it's not only useful in PDE, well, in PDE simply because, as we mentioned before, if you have the derivative of a function and you try to look at the Fourier sequence or the Fourier coefficient of this function, then it's nothing but some multiplication of the Fourier series of the Fourier coefficient of this function, which is why to study the Fourier coefficient or the Fourier series of a function is very useful when you try to learn this differential equation. Okay, it's even better than the Laplace expansion. Why is that? Because if you only have the Laplace expansion instead of the Fourier expansion, you have Sx is equals to the summation of x to the power n an. Okay, so if you try to look what happens to this derivative of this function, what you will find is, okay, you will have a shift of this Laplace expansion or the Laplace series, which makes it like this, right? We assume that everything converges uniformly. So which means it will change the coefficient. Meanwhile, it will do a shift of your coefficient, which means if you want to solve, for instance, f prime of x equals to fx, then what you want to solve are infinite many equations, and one is related to another, because you can see that f prime equals to x, that simply means n times an, which is the coefficient at term n minus 1, okay, which equals to an minus 1. So for the Laplace expansion, if you have this kind of differential equation, then what you get would be this kind of relation. And for this kind of relation, if you want to solve them to solve an, then that is in general very hard. For this one, it's much easy. It's very easy, but in general, it's very hard. Okay. However, if you want to see the Fourier expansion, suppose you can expand a function in the sense of Fourier expansion. Okay. Then what you will have is, if you take derivative of it, then you will have, there is no shift, n times, well, in times an e to the inx. Okay, so if you want to solve a differential equation, what you should have is f prime, for instance, f prime x equals to fx. What you will have is, well, you have in times an is equals to an instead of an minus 1. Okay, so for this kind of differential, well, for this kind of algebraic equation or the system of algebraic equation, it's much easier than this time. Okay, because it is closed by itself. You can only solve them.
Wait, sorry. Can we? So basically, with the a derivative of fx, why did we get n an instead of n I an?
Wait, which one? This one?
Yeah.
This one? Because if you take derivative, you take derivative term by term. We assume that.
Oh, so you first take derivatives of the
So you
term
have
and then
this.
derivatives
Exactly.
of the coefficients. Okay.
Yeah, exactly. So which is why you should have, okay, every term should have some relation with some previous term, okay, which makes the problem harder. But here, of course, this is not a good example because we assume that your f should be periodic, right? So then you don't really have a solution to this problem. But let's assume you have some kind of differential equation, right? And then the differential equation will become some algebraic equation with every single, algebraic equation are independent to each other, right? You will not need to solve an equals something an minus 1 or an minus 2. You only have an, you do some algebra is equals to some an. Okay, so which makes the differential equation much easier in this sense. Okay, so this is why if you are interested in differential equation, do a Fourier transform or try to look at the Fourier expansion of this function is always useful. But of course, this is only useful when you have a periodic function. What if you have the function which is not periodic? This is something we will discuss on chapter 5. Okay, we will discuss it next time on Thursday.
But what kind of coefficients when multiplied by in can be itself?
Yeah, there is no this kind of coefficient. You know.
Okay.
The only thing that is possible is fx equals to 0, right?
So basically, we're saying that there are no kind of like fixed points for it.
Well, you can try to understand it that way. There's no fixed point for the differential operator on the space of periodic function, right? If you have a periodic function, then the derivative of this function shouldn't be the same as the function itself. If you have the periodic function, so the only possible case is fx equals to 0. Okay, this is the only possible case. So this is why the Fourier coefficient or the Fourier expansion is so useful. However, it is not only useful in this sense, it is also useful in some other sense. It is also useful in the sense of some other kind of very interesting problems. By the way, I forgot to mention last time, last time we discussed a lot about the convergence of the Fourier coefficient or the Fourier series. But don't forget, if you don't have some very good condition for the convergence, you may not have the convergence of the Fourier coefficient, right? So which is why we always write the Fourier coefficient or the Fourier series of function f, it can be written as this kind of thing. But we will not use the equal, okay? This only means the Fourier expansion of fx is this form, but they may not equals to each other, okay? Just a remark. Okay, so we cannot, homework, there are some mistake you made, which is you may have a function who has a Fourier series, corresponding Fourier series looks like this, but you cannot say they are equal, okay? Even you have a continuous function, they may not equals to each other. You can check your textbook. There is an example, which is quite technical, that says that there exists some function which is continuous, but the Fourier coefficient of the Fourier series of this function diverge every point, okay? Every point of its domain. And today, I would like to, prove a very well-known inequality. And if you study the mathematical Olympics or the mathematical contest in your high school, then probably you have used it for a long time. But I don't think you do have any vigorous proof of it, okay? Which is the isoparametric inequality. I believe everybody heard about this, the isoparametric inequality, which says that, well, if you have some geometric shape, okay, then if you want, well, some shape with the same parametric of this geometric shape, but with a bigger, well, with a bigger area, bigger than this one, that is possible. Actually, with the same among those geometric shape, with the same parametric, the length of this boundary, with the same of that parametric, the biggest area you can get is when you have the circle. Okay, this is the biggest area you can get with the fixed parametric. Okay, this is so-called the isoparametric inequality. Okay, I think everybody have heard about this. The circle or the disk is the best shape. It can have the biggest area. Okay, but now the question is how you can prove it. Here, based on Fourier analysis, I'll provide you a proof, a rigorous proof. Okay, so for the proof, of course, we are doing something like analysis. So we have to make it as an analysis problem. Okay, so in analysis or in calculus, how you can write a geometric shape in 2D? Well, this is actually a question, right? But I think you have learned something from 201, Math 201, the multivariable calculus. Well, what is a geometric shape on 2D? A geometric shape on 2D or a geometric curve on 2D, closed curve on 2D, is just a parametrized curve. Okay? A parametrized curve, gamma, is a map. Gamma from some reference domain from AB to R2. Okay? For instance, if you have a circle, then this gamma should be unit circle, should be cosine t sine t, where t is your parameter. Okay? T is a parameterization of a circle. So which means this would be your gamma, and gamma depends on t. Gamma is from 0 to 2 pi or minus pi to pi to R2. Okay? Gamma t for circle is equals to cosine t sine t. Okay? And the image is so-called, well, it's so-called the geometric curve. Okay? The image of gamma is a set of points in the plane which we call a curve. And we denote it by capital gamma. Okay? Now you have little gamma, which is the parameterization or this representation of the curve. It represents this capital gamma. Okay? Then, well, if we do have some geometric restriction, on this gamma, for instance, if we want to consider this kind of shape, we want to make it simple. We want to make it easier in the sense of analysis. We say gamma is simple. Well, a curve is simple if it does not intersect itself. Okay, so which means if a curve, we say a curve is simple if it did not have this kind of self-intersection, like an 8, okay, like an infinity, or this kind of thing. Okay, we don't want this kind of self-intersection. And gamma, we say the curve, a geometric curve, is closed if the is two end points coincide. Okay, so if we have a curve like this, then this curve is not a closed curve. Okay, but this kind of curve is a closed curve because from starting point you go along, well, a lot of things, and then eventually it go back to this starting point. So which means if you want to denote those kind of two properties in geometry, a simple curve and a closed curve on our analysis, what we want is we want to ask something about gamma. That is the little gamma, gamma S1 not equals to gamma S2 for unless S1 equals to A and S2 equals to B. Okay, this is the meaning of little gamma is simple and closed. You see that gamma S1 not equals to gamma S2 if S1 is not equals to S2 and is not at the endpoint. Then that means it will not intersect with each other. Well, it will not intersect with itself. Okay, and S1A equal F gamma A equals to gamma B, that simply means eventually you go back to your starting point and make your curve closed. Okay, for instance, this unit circle, the unit circle is well, it's a simple curve because it will not intersect with itself. You can see that it will not intersect with itself. And 2 points will not equals to each other unless they have some, well, gamma, well, for instance, gamma t equals to cosine t sine t. Okay, t between minus pi to pi. And gamma t1 is not equals to gamma t2 unless you have t1 equals to minus pi, t2 equals to pi, or the other way. Okay, so any other t1, t2, well, your gamma t1 is not equals to gamma t2. But if you t1 equals to minus pi, t2 equals to pi, then your gamma t1 equals to gamma t2. Okay, is that clear? The meaning of this geometric shape or the parameterize the curve. That's clear. Any question about it?
Looks clear.
Okay. Then, well, since we have this kind of curve, or we have this kind of well, gamma, little gamma, then of course we can also extend this gamma into a periodic function, right? Like in the circle, we can extend it to be a function with period 2 pi. With period, if you have AB, then it will be with period B minus A, okay? Okay, so that it becomes a periodic function with period B minus A. Because you have this gamma A equals to gamma B, so this will give you, well, if your gamma is a continuous function, then it will give you a good function, which is a continuous function. Okay. And then if you want to calculate now, if we want to calculate the length of this curve, how can we calculate the length of this curve, of this closed curve, or the parameter of this geometric shape? What can you say about it? How can you calculate the length of gamma? I think you have learned this in calculus.
Some kind of integral for lines, which I forgot, but it was something like integral whatever ds.
Yes, that's right. What it is? Yeah, what was it? What's the length of this curve?
Oh, it was, we can try to take a function and then multiply by square root something like derivative x squared plus derivative y squared.
Then what is the function? What is your function?
The gamma? No.
Well,
No, wait.
really, right? Because gamma is a two-dimensional function, right? It maps from an interval to R2. Right?
Guys, help. Guys, help.
What is the length of a curve, of a closed curve gamma? How can you calculate it?
Line integral.
Yeah, it's line integral. It's line integral. Then what it is? How can you represent it by this gamma?
Actually, we take an integral of d of s, and if we want to transfer d of s to like d of t, the relationship is we should multiply the square root of the taking derivatives of
That's a lot. I told it like a minute ago.
Well, you can imagine, okay, how you can calculate the length of this kind of shape, for instance. Well, you can see that, well, the length of this shape is nothing but, well, you try to divide it into a lot of pieces, right? And then try to take a summation of these pieces. And the question is, how can you calculate each of these very small pieces? It's not very hard, right? Each of the small pieces is equals to this by the Pythagoras theorems is this plus this square divide will take square root. Okay, so it is this small pieces, and you take the sum. So which you can somehow write it as this kind of thing. You take the line integral of ds, where ds is just this kind of small pieces of the length of this curve. Okay. Then for small pieces, you can treat it as some straight line, right? So if you try to calculate it, it's nothing but the change in x and the change in y, right? This part has length change in y, and this part has length change in x. Okay, so which means it should be equals to the square root of, if you have gamma, let's say gamma s is equals to xs, ys, okay, then what you will have here, it should be x prime of s square plus y prime of s square ds. Okay, or we can write it compactly. Or we can write it compactly, which is you take the integral from a to b, because you have the s, right? And with gamma prime is a norm of it. So you can treat this gamma prime, the norm of gamma prime, as the unit of your length. Okay. By the way, this ds is different from this ds. Maybe I shouldn't use s again, because this ds is well, is small. Let's call it t. Okay, let's call it t. To make it clear, because in your multivariable calculus, you use ds to denote the small piece of your curve. Okay, and let me write it. From a to b, gamma prime of t, norm dt. Okay, so this is the parameter of your closed curve, simple closed curve. Okay, which I hope is not hard to understand. You just need to look at the small piece of your curve. Okay, what is a small piece of your curve? How can you calculate it? It's just that. Then the question is, how can we calculate the area of the region enclosed by this simple curve? Let's say the area is this, well, this A of the region enclosed by a simple curve, gamma.
Well, actually, polar coordinates might be pretty nice there.
Well, but that's only nice for this unit disk.
But you can change radius and angle changes uniformly, so.
That's okay. But then how can you calculate the area?
Then you would have taken, like, say, some kind of a center, an integral of like radiuses that and the function of radius.
This kind of shape. How can you find the area of it?
Like if you put a dot, say for example, some kind of a dot in the center, and you say the function would be this, yeah, like kind of a function of kind of like a radius. Yeah, and you just take all the angles and you see what the distance is from the center to the curve and just sum all of them. It's an area.
Okay, yeah, that works. That definitely works. That's true. But is that the first way for you to find the area of such kind of domain? In your calculus 1, how can you find the area of this domain in calculus 1? In calculus 1, how can you find the area of this domain? The shadow area. How can you find it? Yeah, it's fx dx, right? Is you trying to write it as y equals to fx. And then, okay, for this part, for this upper part above x-axis, it's just take the integral from this point to this point of your fx. For lower, well, so for everything below x-axis, it should be, you have to have the something like fy equals to gx. Okay, that's a different story. This will be a different story. then, well, if you try to calculate the area of it, you can simply just by doing the integral from some point to some point fx. Okay. However, it seems a little bit hard in general, right? Because, for instance, if you have some point here, if you are always from here to here, then you can only calculate the area between this point and between this line and this line, but not here. So for here, if you want to calculate the area of it, it seems a little bit different from it, right? You may have to treat it as well, x as a function of y instead of y as a function of x, right?
But then you can always draw it so ugly that then you have to do it.
Yeah, you can always do it like that, but then this shape will be somehow tricky in order to find it, right? You have to cut it into a lot of shape and then try to calculate it. However, this is always doable for most of the shape, right? But now what we have is, instead of this kind of functions, what we have is a parameterized curve, right? We have a gamma t equals to cos, well, equals to some xt, comma yt. Okay, so this will be a different story. We didn't really write y as a function of x, neither x as a function of y. We just use another parameter t to be the parameter, right? To do a parameterization. And in this case, it's almost the same as before, which is you can always try to calculate the area like this as well. From A to B, well, you have y dx. Okay, which equals to, and now it's actually t here, right? And it's actually a to b, not really y to dx, but y times x prime dt. Okay, that clear?
Yep.
But if you do the integration by part, or if you try to see it another way, which is you try to see x as a function of y, because sometimes it's y is a function of x, sometimes it's x as a function of y. You can also write it as from a to b, y prime times x dt. Okay, by the same reason, it can be written as x dy. Okay. So both way works. Both can be seen as the area of this curve, the area of this region. Okay, but in our textbook, we just use a little bit tricky way to denote it for some geometric purpose, but we don't really want to discuss about it, which is 1/2 of this plus this. Well, but you can see that if x and y are both continuous function, differentiable function, then these two should be the same. Okay, so in our textbook, he just say that, okay, it's actually equals to 1/2 x dy minus y dx. But if x and y are both smooth, then it's actually the same as x y prime or y x prime. Okay, so it's 1/2. You take the integral from a to b, x, well, x t, y prime of t minus y t, x prime of t dt with absolute value. Okay, so we define this form as the area of the region enclosed by the curve gamma. Okay. Any question?
I have a question.
Mm-hmm.
Why it is negative here?
Well, yeah, good question. Good catch. There should be a negative. There should be a negative sign here. And we should put absolute value here. Otherwise, it doesn't make sense because otherwise you may have some negative area. Okay. If you take the integration by power, you'll find you'll have a negative sign. This too will be a different sign.
Okay.
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 Any other question? That's a very good catch. Okay, now the problems becomes quite clear. That is, we have a closed simple curve, gamma, and gamma closed simple. And what we do want to prove is, well, you have this is a parameter. Let's say this is L. And this is the area, which is A. We want to show that this L, it can somehow control the area. A is less or equal than, the area is less or equal than L squared over 4 pi. Okay, this is so-called isoparametric inequality. You can see the area is less or equal than this the parameter square divided by 4 pi, and it is the equality is true if and only if gamma is a circle. Okay, this is so-called the isoparametric inequality, which is the area for some fixed length, fixed parameter curve has an upper bound. And this upper bound is the area of the of that parameters with a unit circle, with the circle. Okay, and it achieves this upper bound only if you have really a circle. This is so-called the isoparametric inequality. Okay. Any question? Any question? Okay, so if you do not have any question, then let's try to prove it. The proof for this inequality is extremely easy if you use the Fourier coefficient. Okay, let's try to do it. As we said, gamma t is equals to xt yt. Okay, and since we're trying to use a Fourier series and Fourier analysis to study it, then of course we may assume xt is a summation, well, it has a Fourier coefficient an e to the ins. Oh, e to the int, I'm sorry. And yt has a Fourier expansion as vn e to the int. Okay. Then what is this L square? L squared over 4 pi is what?
Well, it's kind of, so we know that L should be like the kind of like a, if we take the Fourier coefficient, it should be like the sum of maybe some kind of square of sum of A squares B,
something like that, something like that. That's correct. If I'm correct, then the sum, well, this, you can use the Parseval identity. Okay, it's actually equals to this. Am I right? Sorry. It seems that I made a mistake here. I'm sorry. So maybe I should need one more step. Then we can use Parseval identity. This step is actually pretty usual when you try to study the analytic geometry. That is, we can do a change of variable. Such that we can change this T to parameter S. And we change it so that we can make it so-called well, what is the name of it? I'm sorry, this is my fault. Let's make it, well, the name of it is, well, this is S, is so-called the parameterization by class, which is you try to make this change of variable, and this S is, well, it's a function of T, and then what you will have is under this change of variable, if you have this, well, from A to B, this gamma prime of T, which is the length of it, you can make it gamma prime of T, gamma prime of S to equals to 1. Okay, so which means it is equals to gamma prime of T is equals to gamma prime of ST times S prime of T dt from A to B. So which means we do a change of variable. We change the parameter of your curve such that we make these two guys multiplication equals to 1. Okay? And well, this is maybe I shouldn't write it this way. I should write it as this gamma of ST is equals to something like eta of T. Okay, and this eta of T with derivative we have is equals to the length of eta of T equals to 1. Well, whatever it is, it's simply just a geometric kind of observation. That is, you have a curve and you're starting from this point and ending at this point, but we try to use the, well, the arc length of this curve as your parameters. Okay, so which means, well, gamma at this point, gamma at 0 is equals to your starting point, and you go through this curve with speed 1. Okay, so that you will have this gamma prime at this point at your parameters s, using your parameter s, is always it's always equals to 1. This is more or less like the change of speed of your gamma. Okay, so in this sense, what we have is well, if you do a change of variable by using this arc length parameters, the existence of the arc length parameters is well, it can be proved by a homework problem for the existence of s, change s with t. Okay, we change the parameters to the arc length parameter. Then in this case, what we will have is, well, the length is actually equals to, you take the integral from 0 to L, and your gamma prime of s is equals to 1, so it's equals to from 0 to L ds. Okay, so we can change by doing this arc length parameter. You can change your parameterization of your curve to be something of this proposition. Okay, this is a trick about the parameterization. And if it is this way, then what we have is, well, you will have this L is equals to something. And this something, you can write it as this way, but you can also write it as, well, gamma prime of s ds with square from 0 to L. Okay, because it's equals to this power 1. It's also equals to the power of 2, because your gamma prime with this parameter is equals to 1. So of course, it's also equals to this guy. So which means it's equals to from 0 to L x s prime square plus y prime of s square ds. Okay. So after you do a change of variable, you change the parameterization of your curve by the arc length curve. Then your this xt yt becomes xs ys with some other functions. Then L is equals to this kind of thing. Okay. So what we have should be, well, this L is equals to this stuff. And then we have another thing, so-called Parseval identity, right? So what we have is what we have is 1 over 2 pi. You take the integral from 0 to L with x prime of s squared plus y prime of s squared ds should equals to divide by L, I'm sorry, because you change the length, because you change the period of your function to be L, right? So it should be 1 over the period of your functions, and well, you take the integral from 0 to L. This function square is equals to the summation of the Fourier coefficients square. No matter what kind of function you have, this xs you have, x prime s you have. And what is the Fourier coefficient of this function's x prime of s square? well, it should be, we'll have the Fourier coefficient I n a n e to the I n s, right? So which means x prime of s, it should have the Fourier coefficient I n times a n, as we said before. So it's equals to this one norm square by Parseval identity is equals to n squared a n squared. Okay, plus n squared b n squared. This is the Parseval identity, right? The average of your functions, well, the L2 norms, well, actually, as a function square, you take the average on your period is equals to the little L2 norm of the Fourier coefficient of your function. Okay, same as y prime. So that means, well, this is equals to what? This is actually equals to 1 is equals to the summation of n squared a n squared plus n squared b n squared. Am I right? I'm sorry, I made a mistake when I prepared this part, so which is why I have to double check that. Sorry about that. Probably I shouldn't write it this way. Probably what I should write is, well, we try to use this kind of well, parameterization, and then we assume that your L, for simplicity, let's assume that your L is equals to 2 pi, okay? As long as we can show when L equals to 2 pi, this is true, then we have nothing more to worry about, because otherwise we don't really have this kind of Fourier expansion, okay? So to make life easier, let's assume L equals to 2 pi, okay? If we make L equals to 2 pi, then this will be 2 pi, and this will be 1 over 2 pi, and we will have 2 pi is equals to, well, 2 pi like this, for simplicity. For simplicity, let's assume that the parameter of your curve is equals to 2 pi. And then we still have this kind of, well, this kind of identity, because we change nothing. And you have this 1 is equals to this kind of thing. Otherwise, if you don't have this L equals to 2 pi, then we still have this Parseval identity, but the expansion here should change a little bit. It should be T, well, it should be S over L, right? It should be S over L times 2 pi, so that it becomes the correct expansion. But then that makes it well, over too long, so I just write it this way. I just assume that L equals to 2 pi, okay, for simplicity. And if L equals to 2 pi, well, what we need to show now is we just need to show the area of this this kind of well, geometric object is less or equal than L equals to 2 pi, is less or equal than pi. This is the only thing we need to show. Okay. For simplicity, we assume that this looks like this. But again, for arbitrary L, this is still true, right? Well, you just need to change here the Parseval identity, and you need to change the Fourier expansion of your function from ins to be ins times 2 pi over L. Okay? Then, well, everything else should be the same. Then, well, of course, the derivative will have another parameter here, which is 2 pi over L in front, which is why you may have something here. But for simplicity, we assume L equals to 2 pi. Okay? Now, what do we have? Okay, now what we have is you have an identity. By Parseval identity, you have this is true. This is true. Now, what is your area? The area of your function of your curve should be looks like this, right? Should looks like this, which is again 1/2. You take the integral from 0 to 2 pi. You can see that we can still change it to be from 0 to L, but that will be a lot of words. So we just from 0 to 2 pi for simplicity. Xt will x as y prime of s minus y as x prime of s ds. Okay. Okay, you want to show this a is less or equal than pi. How can you show that? Well, since we're trying to use a Fourier sequence, it's actually the same as the Parseval identity. We also have some kind of f times g. We take the integral. It's equals to on the Fourier side, you do the multiplication, right? So this is actually equals to 1/2. Maybe you should times pi divide pi. Integral from 0 to 2 pi xs y prime of s minus ys x prime of s ds is equals to pi times the summation of an corresponding to x and y prime is inb minus I will bn times something similar in a. Then we have to cancel. It shouldn't be true, so we have to do one more step. That is, we have to, because this is not really the multiplication of two functions, so let's try to make it multiplication of two functions so that we are able to deal with it by using the identity we have, right? And this is minus, but after we take the absolute value, we use the triangle inequality, so we should have this one. Y as x prime of s ds. Okay, and this is pi times this. We can use the identity we have because this is f times g. We take the integral. So this is, well, the summation of an times y prime corresponding to inb. Okay, plus in times Bn. This is a summation of that. Then it's equals to pi times n an bn with 2, you take the summation. N not equals to, well, n is actually could equals to 0, but then that's actually 0. And from minus infinity to infinity. Okay. I hope that's clear. Although I made some mistake in, well, on this process, but I hope this part is clear. To get it here is clear. Okay, we did nothing, just use one identity we get last time. We did nothing but just use a Parseval identity last time. That clear? Any question? Any question?
I have a question.
Mm-hmm.
How could we like change the variable from t to s?
That's a very good question. How can we change the variables from t to s? Well, remember, what we're trying to study is a geometric object, right? So for a geometric object, of course, you can use different parameterization of your geometric object, right? For instance, this is a geometric object. You could have cosine t, sine t as the, well, for instance, as a parameterization of a disk, of a unit disk. But you can also have cosine 2t, sine 2t as the parameterization of your unit disk. Okay? The only thing we have to guarantee is, well, after we do this parameterization, we still get the same image of your geometric object. Okay? So which means we will at the very beginning have gamma t, which equals to xt, yt. Then, as long as we could have some functions s, such that, well, when you have this t from a to b, you can have s, from a to b. Then you could change t to be s, and you still didn't change your image of your gamma, right? And similarly, you can also try to do a change of variable or the change of parameters by saying that we can change gamma to be gamma t to be gamma eta s, right? When s range from some period, like from 0 to L, gamma s range from A to B. If that is true, then it's also okay, right? We still get the same image as a geometric object.
So basically we need to change, like after the change of variable, we need to make like the r prime of s, like the norm equals to 1, right?
Exactly. So if we try to find such kind of eta s, which eta is a function, eta will maps 0 to L to AB. And well, we can actually make this eta to be a bijection. And it's a smooth bijection. You can actually make it like that. Such that you can see then the image of gamma doesn't change. And now what you require is, after you take the derivative of this guy, gamma prime of s, so which equals to gamma prime evaluated at eta times eta prime. We want it equals to 1. So as long as such kind of eta exists, then, well, you do have this change of variable, right?
Okay, thank you.
So we just want this kind of eta. But the existence of such kind of eta, well, it's not very hard to prove, but you will need some other kind of well, regularity of your gamma. We'll assume that our gamma is good enough. We will assume that our gamma, because the gamma, we will assume that our gamma prime, our curve, is not equals to 0. Otherwise, this change of variable, change the reparameterization by arc length is not valid. Okay, we'll assume that this is true. This is one condition about the regularization of our geometric curve. But this, in geometry, we always assume that. If a curve doesn't satisfy this condition for any t, if a curve doesn't satisfy this condition, we say this curve is kind of very weird. Okay?
Yeah, got it.
In general, we will assume this is true. Okay?
Thank you.
And then after this change of variable, you can see that everything is quite clear, because everything is just you change the integral of a function to the summation of the Fourier coefficient. Okay. Any other question?
Professor. On the left side, the second step, it seems that you multiply the
What? I'm sorry. You mute yourself. Hello.
Oh, sorry. So by definition, I think what we get from this step would be the Fourier coefficient of like xs multiply y prime s. So does that mean that the Fourier coefficient of a product is a product of the Fourier coefficient? Because it seems that you do.
Yes, we proved that last time. Our textbook on chapter 3, we proved this kind of propositions and like this, right? The product of these two functions, you take the integral, is equals to the product of the Fourier coefficient, and you take the sum.
Okay, I can only remember the convolution.
This is not a convolution. This is well, this is actually the proposition corollary to the Pascal identity. Okay. But this makes our calculation much easier, because you don't really need to calculate the integral. You only need to calculate term by term, do the summation. Okay. And if you agree with that, then you can see that this is less or equal than this. All right, by whatever this averaging inequality or the mean or whatever, this each term is less or equal than this each term. So it's less or equal than pi times the summation, and from minus infinity to infinity, this is n squared a n squared plus n squared b n squared. Of course, this one, you don't really have this one, right? What you really have is n times a n squared plus n times b n squared, right? And it's less or equal than this guy, because n is not equals to 0. N is greater or equals to 1. Then of course n squared is greater or equal than n. This equals to pi. Okay, so we prove that this area is less or equal than pi. just by one step of inequality. Okay, is that clear for this part? For this inequality here? And you can see that this inequality is true if and only if and only if, well, you should have n equals to 1 or 0. Okay, or xs is equals to a minus 1 e to the I ns, n equals to 1 with minus I plus a0 plus a1 e to the is. And ys is equals to b minus 1 e to the minus is plus b0 plus b1 e to the is. Okay, and that clear? So we must have n must equals to n squared, if that is true. Right? This is the first thing, it must be true. And secondly, we must have this equals to this. Right? So an's norm is equals to bn's norm. So that means, okay, a1 f's value is equals to b1's f's value, a minus 1's f's value equals to b minus 1's f's value. By a0, it disappears, right? A0 and b0, they just disappear. You don't have the constraint on a0, b0. And moreover, we are in R2. So x, y are both real. Right? So which means a minus 1 is equals to a1 bar, b minus 1 is equals to b1 bar. Right? Then we are almost done, right? We only need to solve this kind of thing and see whether it is something like a cosine some theta, sine some theta. Cosine some theta, xs is cosine some theta, ys equals to sine some theta. Then we are done, right? Okay, we're almost done. And we also need to have the summation of n squared, a n squared plus b n squared is equals to 1. That means you only have n equals to 1 and minus 1, right? So that means you must have 2 times a1's norm square plus b1's norm square, because a minus 1 equals to a1 bar, b minus 1 equals to b1 bar, so they have the same norm, is equals to 1. And they also have the same norm, so that means a1 square must equals to b1 square equals to 1/4. So that means a1 equal, well, they must both equals to norm, must both equals to 1/2. Okay? So that means we can assume that a1 equals to 1/2 e to the I alpha, b1 equals to 1/2 e to the I beta. then that means a minus 1 is 1/2 e to the minus I alpha, b minus 1 equals to 1/2 e to the minus I beta. We are pretty close, and we also know that the area equals to pi. Okay, so that means you must have this this kind of thing equals to this kind of thing equals to pi, right? So what you should have is, if you try to plug in and try to do the calculation, you'll find that then alpha should not equals to beta. I'm sorry, alpha sine alpha minus beta should equals to 1 with absolute value. I don't want to plug in, you can plug in, because you want this term equals to this term, right? We want this to be an equality as well. So that means alpha minus beta should equals to, well, half pi, half k pi, k odd. Okay. So what can you say about it? Well, you can see that xs then should be a0 plus, this is a minus 1 is e to the I minus I alpha, this is e to the I alpha, so it will gives you cosine alpha plus s. And the ys is equals to b0 plus cosine beta plus s. But beta is equals to alpha minus a half k pi, so it's equals to b0 plus sine plus or minus sine alpha plus s. So we get alpha minus a0 squared plus y minus b0 squared equals to 1. Unit circle. Okay.
Professor.
Mm-hmm.
So I mean, when we talking about when the equality holds, and I'm a little bit confused why the n can only be 0 or 1.
Well, because you see, if this inequality is an equality, then that means every step we make less than equals to, it must be equals to, right? Which means this must be equals to this first. And secondly, well, this is actually equals to, okay? This is just an identity. This, well, this is also equals to, this is also an identity. So this must equals to this, right? So that means an's norm equals to bn's norm, okay? And you only have n here, but you have n squared here. N squared is greater or equal than n. So you must have n squared equals to n, right? Otherwise, this will be a strict inequality. This is n squared, this is n.
But I think I think by the square, like by the square formula, this we can get this inequality directly instead of like introduce n here as a coefficient.
You see, this is a n bn. It's less or equal than n squared bn squared.
Yeah. Yes.
And you have one n here, right? What do you mean you will have this
I mean, if I take like n times the absolute value of an plus minus n times the absolute value of bn squared is definitely larger or equal to 0. And expanding it, we can also get the same result and without.
No, you will have square. You have some squares here. Okay, you see, you only have one n here. If you want n square here, then you should have n square here as well. Right? You see, here I only use one. This is 2n times an times bn. Okay?
Yes.
And it's less or equal than n times, we take n outside, an squared plus bn squared. Right? We only use this. And if you say that, okay, of course, it's less or equal than n squared times an squared plus bn squared, but an squared plus bn squared times n squared times n squared, if you use this kind of inequality, it's greater or equal than 2n squared an bn. Right? This is something you should get by the average inequality.
Okay.
Though you have additional n squared here, not n here, which is why you have n squared must equals to n.
Yeah, for sure. Thank you. I understand it.
Mm-hmm. Any other question?
Or but could you explain again, like why do we need to make a less or equal to pi? Like on the previous page.
A less or equals to pi.
Yeah.
Well, where is? Oh, this one.
Yeah.
Because you see, we want to show this one. We want to show this one. When L equals to 2 pi. When L equals to 2 pi, then we plug in, we got, okay, A is less or equal than pi.
Ah, okay, I see.
We assume that the parameter of your disk is equals to 2 pi. That means it is a unit disk. We assume it is a unit. Well, if the maximum area is a unit disk, then of course this area is pi. The maximum area is pi.
Okay, I see. Thank you.
So the proof I go is not very smooth, but the idea here you can see is very straightforward by using the Fourier coefficient and Fourier this kind of pathwise identity. You can prove it, well, only by this kind of inequality. But the setting up is not as easy, right? So let's have a 10 minutes break. I'm sorry for the late, but let's resume at 48, okay? Sorry, I made a mistake for this problem. Well, that isoparametric inequality is an example I would like to provide to you so that you can see it is very useful to do some Fourier analysis in general. And even more, if you try to read your textbook, you'll find that, well, Fourier analysis is actually quite relevant to also number theory. It's a so-called analytical number theory. Of course, at this moment, you may not be able to answer any questions in number theory, but after you learn, maybe after you finish the second book of the STANS, this textbook series, the complex analysis, you will be able to prove a lot of things. One of the most exciting thing about this Fourier analysis and the number theory is you can use it to prove the prime theory. You know, the estimate of how many prime numbers you have, less or equal than capital N, the prime theory, which is a very nice theorem, and someone even says that every mathematician should know how to prove it. Otherwise, you will lose 10 years of life. something like that. Okay, you can try to read it. This is on the second textbook, the complex analysis. So let me try to do a very quick review about what we have learned in this half session. Okay, and we basically learn 4 chapters of our textbooks. First, we learn the chapter 1 of Strasbourg and Stan's book. They both talks about, well, how you can get some PDE. So based on that, what we learn are something like, what is a PDE? PDE is just something with partial derivative, okay? And what is the order of PDE? Is how many derivatives you take. What is linearity? Linearity. Because linear PDE is much easier for us because we can try to find some solutions to do some superposition principle. Okay, and what is initial value and boundary values, or initial conditions and boundary conditions? Well, those are more or less like a physical constraint about your PDE, which is why sometimes we'd better know the background of PDE. As I said, every PDE is just a story. If you want to understand it, about how to solve it, about how to set it, what does it tell you, then you have to know the background of it, the meaning of each term, or the meaning of the global thing, okay? And then the very important thing about PDE is the 4 important types of PDEs. The transport equation. Transport equation is the first thing we've learned, and it's linear, it's first order, it cannot be easier, right? And how to solve the transport equation? And how to understand it, or how to visualize it. What is the characteristic line of this transport equation? How you can understand it? It's just the level set of your solution, okay? And the Laplace equation, and the heat equation, and the wave equation are the 3 types of second order linear PDE we've learned, or we are going to learn, okay? And in chapter 1, we learned that how we can find them, or how we can get them. Where do they come from? Just by some very easy or kind of easy physical situation. Right? We use some kind of control volume method to get those kind of equations. And then we also learn how to use the D'Alembert solution, D'Alembert formula to solve wave equation on whole space. How to use that formula to solve it? Well, formally. And what does it tell us? It just tells us, okay, the change of variable, it might be very important. Okay? And what about in general? After that, we learned that, how about in general? We have another PDE with, well, maybe wave equation, but with boundary condition. That makes sense. Okay? And we find that then probably we should try to study the boundary conditions Fourier expansion, right? We probably need to do some Fourier expansion and then try to show some kind of convergence. And then we also learned that the Laplace equation. And by the way, I forgot to mention, if you have this kind of problems, just as the problems in your homework, then if you try to solve it by the Fourier series or Fourier expansion, well, the basic method, the basic step would be, you first try to do the separation of variable. You try to dream the best or the ideal solution. Then you try to use the superposition principle to do some approximation. See whether it's possible or not that your dream comes true. Okay? And also, we also learned that we may need Fourier expansion or Fourier series in order to study this kind of this kind of wave equation or Laplace equation using the separation of variable. Then we need to introduce what is a Fourier expansion or Fourier series of a function. Then the very basic thing about the Fourier series is how can we understand it? What is a Fourier series of a function? As we have learned on chapter 3, we learned that, okay, for a Fourier series, it's nothing more than, this is chapter 2 and 3 on STEM. It's nothing more than some expansion or some representation in vector space by some kind of a basis, like En. It's nothing more than you try to write F as a summation of inner product of Fen times En. Okay? And another very important thing, which is also our initial, our motivation, initial motivation of the Fourier series is, what can we say? We discuss a lot. What can we say about the convergence? What can we say about the convergence of the Fourier sequence or the Fourier series of a function? We know that in general, if you only have a continuous or integrable function, the Fourier series may not converge. Okay, you can check the example in our textbook. Then, what kind of condition may guarantee that you will have a convergent Fourier series? We learned several things. First, we learned that, okay, if we know f continues and the Fourier coefficient of f converge absolutely, then Fourier series of f converge to f. Okay? And the second, if we know that f is, well, is of C2, which means it's a second order continuously differentiable, then we know that the Fourier series will converge. Right? And thirdly, we know that, okay, what else? Convergence we know? Thirdly, we know that if in some situation, what do we know about the convergence of Fourier series?
If a function is integrable and the kernel is good, then it's...
Yes. If the function is integrable, only integrable, then we know that some other way, which is like an averaging of the Fourier series will converge. Okay, the Chesello means of Fourier series, the Chesello means of the sum of the Fourier series will converge. Let's say the Fourier kernel convolved with f will converge, and if f continues, well, this will converge uniformly. Okay, and also we know that if you have the Poisson kernel, which means it's the Abel means of summation, it will also converge, right? If f is continuous, then this Abel means of convolution or the Abel means of Fourier series will converge uniformly for any f continuous. Right? And on chapter 3, we also learned that if you don't consider this well, pointwise convergent or uniform convergent, you also know that the Differential kernel, although it's not a very good kernel, but under the norm we have, it will converge. Right? But this doesn't mean anything. This doesn't mean the point-wide convergence. It just means some global convergence. Okay? And as some corollary, we also learned that if f is differentiable and the derivative is integrable, okay? It is differentiable, then we know that at all the point that f is differentiable, we have dn convolved with f minus f at this point converge. Okay? Continuously differentiable, I think differentiable at x0, then we have it converge. Okay? So basically, that means we can even get some better result than this one. This one just says that we have, well, our function is twice continuously differentiable. It is converge. It for sure converge. But now we can make it weaker so that if it is differentiable, then it converge. So the only thing we cannot guarantee that the Fourier series converge is, well, if you only have a continuous function, we may not have the convergent of your Fourier sequence, but the Fourier series, but we have it converge in this means, and well, in this means, in this Chesello means, or in this Abel means, okay, but not in the usual way. Okay, so these are the basic things we have learned on this well, 3 chapters or 4 chapters. Any question? Any question?
I think all the contents will be covered in the exam.
Yes, everything I'll assume you know. Okay, all this kind of thing I mentioned are something I assume you know.
Okay, thank you.
I may not assume you know how to prove them, especially if there are some very technical proof, like how you can prove this kind of thing, but I will assume you know that. Okay, because know this kind of thing are very important. What kind of condition can guarantee that your function will converge? Your Fourier series will converge. As an example, there is a problem in your homework, which most of you didn't do it correctly. Is this one. You can check your homework is already on Sakai. You can download it, and it's on page 59, problem number 6. It says that your f theta equals to the f value of theta. Okay, you can see that this function is not twice differentiable, at least at one point theta equals to 0. Okay, but it is continuous. And then the problem asks you to show that by calculation, the Fourier coefficient of f should equals to pi over 2 if n equals to 0, and minus 1 plus minus 1 to the power n divided by pi n square if n is not equals to 0. Okay, this is not very hard. You just do the integration by part, and then you can get it. And then what you can find is, well, he asks you, this is the first sub-questions, and the second sub-question is, well, he asks you to write it in terms of sine and cosine. This is also not very hard. You can try to do a rearrangement, and then, well, you can just get that. This is something I'll discuss later. The third one, he says that take theta equals to 0. We get the summation of all the odd number of 1 over n squared is equals to pi squared over 8. And moreover, for all the n from 1 to infinity, 1 over n squared is equals to pi squared over 6. Okay? This is a very interesting result, because I believe you have learned this kind of series, and then you just know it converges, but you don't know whether what's the value of it. But from this example, from this problem, he just tell you what is the value of this summation, okay, which is really amazing. But then how you can show this? Well, of course, you can show it by, okay, taking theta equals to 0, and you should get f theta, because you don't really know whether it's converge or not. F theta is equals to pi over 2 plus the summation minus 1 plus minus 1 to the power n over pi n squared e to the I n theta. Okay, n not equals to 0. You just know the Fourier expansion of this f is equals to this. But f is not twice differentiable. And if you don't prove that this f is equals to this, you cannot use it. Okay? So let me ask you a question. F has the Fourier expansion like this. For this example, for this particular problem, do we know f theta is actually equals to this? Do we know this?
We can prove it by.
How can we prove it? Yeah.
The sum of the Fourier coefficients converges, so this should converge uniformly.
Yes. So we can use the first convergent proposition of the Fourier coefficient, right? Your function is continuous, and you know that the Fourier coefficient of it converge absolutely is equals to the summation of 2 over pi 1 over n squared, and it's not equals to 0, and it converge. So we know that f theta indeed equals to the Fourier expansion of it at any point, because your function is continuous. Okay, then we can plug in. theta equals to 0. Okay. Or maybe I shouldn't say uniform. It's not really uniform. It just converge for any point. So we can plug in theta equals to 0. This is still equals to f0. Okay, then you can do the calculation and find the value of these two guys. So this is something I would like to say as an example. So you have to know under what condition, at least under what condition, the Fourier coefficient may converge, or under what means the Fourier coefficient will converge. Okay? Any question about this problem?
I'm more interested in another problem.
Okay, we will go through several other problems. Let's start from the very beginning. There is a problem number I'd like to discuss about problem number 3 of chapter 1. Okay, this is a problem about if you have a complex number, omega n is in Cn, is in its complex number, and he wants you to show that Cauchy sequence of the complex number is still converge. Okay, for this problem, maybe some of you misunderstand it. Well, you could assume you know, because I know most of you may learn this. Cauchy sequence of real numbers will converge. Okay, you can use this result in order to show this problem. Okay, so he just wants you to prove those kind of results by using for complex number. By using the corresponding result of the real number is totally fine. Okay. So which is why some of you made some mistake of the second part of the problem. It says that, well, omega n is a Cauchy sequence if and only if well, it converges. Okay, so Cauchy sequence is equivalent to say it converges. And if you have the convergent sequence, then it will be a Cauchy sequence. This is easy to show. But if you have a Cauchy sequence, a complex numbers Cauchy sequence, it will converge. Then in order to show that, it is not very trivial to say, okay, we have a limit, so it will converge to this limit. The existence of the limit is guaranteed by the I think it's Bolzano-Weierstrass theorems, right? You've learned this kind of theorems. And so if you want to show that this Cauchy sequence will converge on C, you have to use that theorems. Okay, you have to use that theorems. Otherwise, the existence of the limit is very non-trivial stuff. Okay, you can either use the Cauchy sequence of the real numbers converge, or you can use the Bolzano-Weierstrass theorems. Okay, if you use the Cauchy sequence of the real number converge, then you can find the limit. The limit is just the limit of the real part plus I times the limit of the imaginary part. But you have to show that, okay, that is also a Cauchy sequence. The real part and the imaginary part is also a Cauchy sequence. Okay. Is that okay? Any question about this problem? Because I see that most of you are able to solve it. So I don't want to go to the details for this problem. I just want to give this one remark about this problem. Okay, any question?
I remember when I am proving this, I just said that because C is similar to R2, so and Bolzano-Weierstrass theorem holds in R, so I said that Bolzano-Weierstrass theorem holds in C. Is that okay? Because I think that's not rigorous.
It's not very rigorous, but it's also fine because you mentioned that you can use the result in R. This is well, as long as you know how to use the result in R, it's okay.
Okay.
Because for this problem, I just want you to get more familiar with the epsilon delta language. Nothing more than that. Okay, and the Cauchy sequence. Okay. Any other question? And another problem I would like to mention is the problem 1, chapter 1. The only problems in chapter 1. Okay, so this problem, he just asks you to solve the boundary value problems for heat equation, for the Laplace equation on not a circle, not a disk, but on a rectangle. Okay, so here is u equals to 0, u equals to 0 on the right and left, and u equals to f1, u equals to f0 on the top and bottom. Laplace u equals to 0. Okay, this problem, he asks you to solve it. Since he asks you to solve it, then you have to solve it step by step. Very careful. Okay. For instance, well, what we did for the disk or for this wave equation is always like we will assume that u can be done by something like separation of variables, which means uxy can be written as capital Fx times capital G of y. Okay, and this would be the first step. You try to solve it. The logic here is you try to solve it, but you don't know how to solve it. So you try to find some special solution. Not necessarily satisfy your boundary condition, but some special solution. Okay, and then you can find that f and g satisfy f double prime over f is equals to g double prime over g with minus sign is equals to lambda. Okay, then the question is, well, you have this lambda, but you don't know whether this lambda is negative or positive. You have to argue it. You have to argue whether lambda is a positive number or a negative number. Okay, and how you can argue it? You find that on x, your f must satisfy this boundary condition. This is something you try to approach, right? You try to approach, you fix the boundary condition on x, and you just release the boundary condition on y, so that you may get a better candidate of the solution. Okay? So which means we don't want our special solution satisfy our boundary condition on y direction. We just want it to satisfy in x direction. Okay? Then we find that, okay, lambda must be a negative number, because if it is positive, then we cannot get, well, x equals to fx equals to something equals to 0, fx equals to another thing is still equals to 0. Okay? So that means lambda must be a negative number. It cannot be a positive number. Okay. This is 0, this is L. Is that 0 pi. Otherwise, we don't really have this lambda is less than 0. So because of f0 equals to f pi equals to 0, we must have lambda is negative number. And we know that f0 equals to f pi equals to 0. So that means if we try to write down the solution, we have f is equals to a times, cosine square root of lambda x plus b times sine square root of lambda x. Okay, we want, f0 equals to 0, f pi equals to 0. This means that the square root of lambda should equals to an integer, right? Otherwise, we don't have this kind of condition. So that we want this lambda, square root of lambda equals to m, or lambda equals to minus square root of minus lambda equals to m, then lambda equals to minus m squared. This is a logic. This is why you want to take, or you have to take lambda to be minus m squared, where m is an integer. Otherwise, it doesn't really make sense. Why don't you guess at some other condition? Why don't you guess lambda equals to something else? Okay? And when you get this lambda equals to minus m squared, then you find that based on this boundary condition, this term should disappear, and you must have this kind of, f equals to this kind of thing, and then g is equals to something like a times e to the y plus b e to the minus y. Okay, and he used some very scary notation here, but you can see that we can also write it in terms of that, right? We can write g in terms of e to the y and e to the minus y. We can also write it in terms of sinh and sinh something else, right? We can write it as a times sinh, sinh y. I'm sorry, this is my and minus my. Sinh y, a times sinh y plus b times sinh my, m times 1 minus y. This is not a problem, right? This is not a problem. Then you can try to match this, this kind of solution to do a linear combination of this solution and match it with the boundary condition in y. Then you find that, okay, if you want to match them, you just need to have this, this u have this form, and since this f0 and f1 has a Fourier coefficient, this, we will assume that it's converged uniformly, and so this u is also has this kind of form of solutions, and this convergent is uniform convergent. Okay, and you have this u is indeed a solution. Although all the stuff you did before that is just a guess, and eventually you find that you should have this kind of expression. Then you find that this expression is actually converged uniformly. So that means your u, although we just do this kind of calculation formally, but since it converges uniformly, so this u satisfy our conditions, or satisfy our PDE, and satisfy our initial condition or boundary conditions. So eventually you have this u is indeed a solution. Okay, so the logic here is we try to find some special solution, and then we try to use a superposition of this of the solution you find to do approximation of the real solution. But then eventually we did the approximation to the real solution, but we don't really know whether this approximation is good or not. just as we did before. We don't know formally we have this approximation, but we don't really know whether it is a solution or not. So eventually, we still need to check whether it is a solution or not. Okay? So 3 steps when you're trying to solve the initial value problems or boundary value problems. First, you try to make a guess about what kind of functions could be a special solution. And second, you try to make an approximation of the real solution, okay, by using the superposition principle. And thirdly, although you try to use approximation, you have to show that, okay, your solution, the candidate of the solution candidate is indeed your solution by showing it converges uniformly. Okay, is that clear? Is that clear?
So,
Sure.
doing that, like we still need to, like for the last step, we need to show that like the sum of all those.
Yeah, but yes, I think for the last step, you should say that. But in our textbook, it didn't really say that. So I assume that F0 and F1 are smooth. And for this example, and I don't take off any point from you by not checking this U is actually a solution. Okay. But in general, we should check whether it is indeed a solution or not. Whether U equals to this kind of thing is really an equal or just some formal expansion.
Okay, got it.
This is very important. This is just what we did on chapter 2. Right? On chapter 2, we just know that the formal expansion should be the formal solution for Laplace equation on the unit disk should be looks like that, right? But eventually, what did we prove? We proved that yes, indeed, and actually any solutions you have, any boundary conditions you have should have that as a solution by showing it's actually converged. It's actually converged uniformly. Okay, so that's the end of the story about finding the solution. You may get something formally, but that formal solution may not be the real solution. Okay?
Yeah, I see. Thank you.
So let's see another problem. Let's see on chapter 2. Chapter 2, number 2. For this problem, I just want to say one thing. He says that, okay, you have this f theta, it has a Fourier coefficient, and then, he wants you to write it in terms of sine and cosine series, which is very usual in some other literature. Okay. Okay, and to write it this way is not very hard. You just combine the positive n terms and negative n terms, then you get this naturally, very naturally. Okay, but don't forget this is still some kind of formal expansion. Okay, and this is the first step, and the second step is he says that if f is even, then we should have f hat of n is equals to f hat of minus n. So that we only have this cosine term, the sine term disappear. Okay? If you want to show this, it is very important to show this is true first. And then you can see that, okay, this term disappear, you only have this cosine theta. Intuitively, that just means that the odd part of the function disappear. Because the sine theta is an odd function, it disappears, then the only thing left would be this cosine theta. Okay, but that's just intuitively. And if you try to check that by multiplying by multiplying sine theta and take the integral, Well, that doesn't really make sense because you don't really know whether this function equals to this or not. So you cannot assume that f theta is equals to this expansion, okay? So in order to show this, you have to go back to the definition of f hat n and f hat minus n. F hat n is equals to minus pi to pi, 1 over 2 pi, f theta e to the minus in theta d theta. Okay, you want to show is equals to f hat minus n, which is 1 over 2 pi minus pi to pi f theta e to the minus n in theta d theta. What you're trying to show is these two are equal to each other, not from the expansion. Okay, not just from the expansion, we see it must be even. So this term, all this term must disappear. So this term must equals, this must equals to that, right? Remember, f theta not equals to this one. It just have the expansion like this. So does C, well, when f is odd, then you must have f hat of n is equals to minus f hat of minus n. Okay, you will need to show this expression, this integral expression, they equals to each other. So that's D, well, this I think I already did well, which is f theta plus pi equals to f theta. Then we can conclude that f hat n equals to 0 for all n odd. Okay, and for E, f hat n with bar is equals to f hat of minus n if and only if f is real value. Okay, don't forget this is if and only if. Okay, so again, what you want to show here is not you take bar, well, you take bar here and you find that, okay, this must be real, so this must be real, this must be real. This is not enough. Okay, because you know f theta is not equals to this expression. So this is real, doesn't say anything about whether f is real or not. You still need to say f is real, that means f hat is equals to f. This is the reason why we say f, or this is the equivalent condition about f is a real value function. Okay, this is a condition. So if you want to say f hat of n with bar is equals to f hat of minus n, you have to do the calculation as well. Okay, it's minus pi to pi 1 over 2 pi e to the in theta f theta d theta. You want to take bar here and want it to be this f minus n, f hat minus n. So you take the bar here, everything else is just a real number. You can take the bar inside like this, right? So it's equals to 1 over 2 pi minus pi to pi. Well, you can split this bar, and it becomes f bar here, and e to the minus in theta, we take bar is e to the in theta, d theta. Okay? So you can see that this will, if f bar of x equals to fx, then this f hat is equals to f hat of minus n, because this is equals to f theta. Okay? On the other side, if f hat bar is equals to f bar, what you can find is f bar minus f has 0 Fourier coefficient. Everywhere. Right? So you get f bar of x equals to fx. By the uniqueness of the Fourier or by this, well, what is that? By the uniqueness of the Fourier coefficient. Okay, if you have a function has 0 Fourier coefficient, then this function must equals to 0. Okay, this is a proof. Otherwise, I don't really know how to prove it very rigorously. Okay. Any question? Any question? I'm sorry, I'm a bit well, of delay of our class. So if you have some other thing you need to do, you can feel free to go. And I will just go through last problems of the homework. And after that, you can ask me any questions if you want. But I will just go one last problems of your homework that I prepare to go. Other than this problem, I just can see that everybody did well, which is the problems number 2 of chapter 2. Okay, I think most of you did quite well, but it seems that nobody really solved the last part of this problem. Okay, which says that if you have the Dirichlet kernel, then what you can show is, okay, if you consider the integral of this Dirichlet kernel, 1 over 2 pi of this integral of the norm of this x value of Dirichlet kernel, you can show that this integral is greater or equal than c log n. Okay, and he gives you a very nice hint, and I can see that everybody are able to show this. This integral of Dirichlet kernel, it actually should converge. It diverges, the integral, as n goes to infinity. Okay, and for part B, he wants you to show that, well, actually Ln is equals to some constant or pi 4 over pi square log n plus something bounded. Okay, for part B, he wants you to use it to construct a function that who is continuous, but the Fourier series diverge at point 0. Okay, he wants you to consider some functions gn, well, actually function g, such that this this kind of function, it will well, he wants to have some fn such that this Sn fn at 0 is greater or equal than some log n, and fn continuous. So which means it's somehow at the origin, this fn, although all of them are continuous, but fn, the Fourier series of fn will be super big. Okay, will increase, will be arbitrarily big. Okay, so the idea he have is, okay, you know that this dn is some function which oscillates a lot. It will oscillate a lot, and so that if you take the absolute value, then everything will flip on, and then it will be very big. Okay, so if you want to make this kind of convolution somehow looks like this Ln, it's very easy. You just need to choose Gn to be this is so-called the sine of your Dn, the sine function of your Dn, which equals to +1 if Dn of x is greater than 0, greater or equal than 0, is equals to -1 if Dn of x is less than 0. Okay, it can be the sine function of the Dn. then we know that gn of x times dn of x, you take the integral from minus pi to pi, is equals to the integral from minus pi to pi, the absolute value of dnx. Right? It is actually equals to, because it just will just make it to be this dnx. Or maybe this is not so clear. So dnx, there is another expression of it, is dnx divided by the absolute value of dnx. Okay, if dnx is not equals to 0, is equals to 0 if dnx is equals to 0. Okay, this is a sine function of this dnx. Then, well, this is totally fine. It's not a big deal. But then the problem is this function, this gnx, is not continuous. It's 1 minus 1 minus 1 1 minus 1 1 minus 1 1. So the problem is, how can we do approximation of this gn such that, well, it will be close? We want to find the approximation of g. Gn, okay? Such that this approximation of gn, say hn, to approximate to be very close to gn, in the sense that gn dn of x minus hn dn of x dx is very small, or at least is bounded about by some constant. At least it cannot grow faster than log n. Okay, so this is some function we want to find. This is some approximation we want to find. So what is this hn? How can we find this hn? Well, it's actually not that hard, but the only thing you have to worry about is dn is not a bounded function, right? So if you try to use the lemma 3 of our textbook, lemma 3.2 of our textbook, we can only know that gn of x minus hn of x, you take the integral, it's very small, right? It can be arbitrarily small. But then this dn will be super big, right? Although it's not infinity, but dn could be very, very big. So which means if you want gn of x times hn of x, well, minus hn of x times dn of x to be small, you cannot take this term out directly because it has no upper bound from minus pi to pi. The maximum value of dn is actually infinity from minus pi to pi, right? Because dn is equals to sine n plus 1/2 x divided by sine 1/2 x. So when x equals to 0, or when x is very close to 0, it may have a, well, it may, oh, I'm sorry, yeah, it may have some maximum value, right? But it could be something not so small. It could depend on that, right? So you may have to show that, okay, this dn of x is less or equal than, well, we can imagine it's less or equal than n plus 1/2 or something like n, right? Then that means if dn of x is less or equal than n on this whole interval, then we can choose epsilon to be equals to 1 over this number, right? We can always choose Hn close enough to Gn in this sense. Okay? Then we know that Hn is continuous and Hn, these two guys, the subtraction of these two guys are bounded above, so which means they are pretty close. And we know that this guy is greater or equal than log n, c times log n. So we know that Hn of x times dn of x dx is also greater or equal than some other constant times log n. Or is greater or equal than c times log n minus this constant c by triangle inequality. Okay, so which means this h is continuous, Hn satisfy Gn minus Hn is less than 1 over n plus 1/2, and Hn times Dn is greater or equal than c times log n. Okay, this is how you can make this Hn or Fn. In this example, he said it's Fn, so this is Fn. Okay, so this is the idea. So you must be able to say something about what kind of approximation you want. In particular, how good approximate you want. Okay, so this is how to solve this problem. Any question?
Could you possibly come up with another solution that would be like more linear, like a sequence?
Yes, definitely. You can choose Hn even explicitly. Okay, how you can choose it, like how you can choose it to be explicitly? You can choose it to be 1 here minus 1 here, but in between it is just a linear. Okay, so which means you can choose Hn like this kind of function. And you can see that although this function may not be very good, it's not smooth, but it's always continuous. And as long as you have this part to be small enough, this is something you can choose to be small enough, to be very, 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 very small. For instance, it can be something like, well, because it oscillates n times, this sine n plus 1/2 x will oscillate n times. Well, in one period, it will oscillate n times. So you can choose this part to be super small, like 1 over n plus 1/2. Okay. Or it could be something like this kind of thing square, whatever. It could be very, very small. Then what you can do is you can still do an estimate about the difference between these two. Well, then the difference between these two are just this kind of function, right, times dn. Okay, and you know that dn is not very small, right? dn is less or equal than, it's not very big, it has an upper bound. Maybe I should say cube here to make it, well, I don't really need cube, I only need square here. So dn is not very small. So which means the integral on this kind of transition area is just like the maximum of dn times the length of this transition area, right? So it's n plus 1/2 times the length of this transition area, and this transition area is at most n plus 1/2 that amount of transition area. So totally, you will have the total length of the transition area is 1 over n plus 1/2. And the maximum value of dn times the total length of this transition area is less or equal than 1. Okay? So you still get this is less than c. But it's more explicit. This kind of approximation is very useful, I think. Okay, does that answer your question? Well, Aya?
Yes, I think it, but also another question. I think at some point, there is a theorem that we can approximate some kind of a function f with a sequence of continuous functions. And so
yes, that's lemma 3.2, which is why I can claim that this is true, right?
yeah, but wouldn't its existence already be enough for we? Oh, because we have to prove because d is big, so we have to. Okay. See.
Yeah, we can always guarantee that given Gn, I can find an Hn such that Gn minus Hn is less than this epsilon with you take the integral. Okay, and this is actually the construction of Hn. How you can construct for this particular Gn, how you can construct Hn. This is the idea. And moreover, you can actually make it even smaller so that you can find some kind of very good function, and with this kind of good function, you can make this dn to be uniformly very big, the integral. But that's another story. Okay, this kind of function is just the idea of how you can build this kind of approximation of a function, of how you can build this kind of characteristic function as you faced as in exercise 9. Okay, how you can approximate a function which is a characteristic function. Okay, and you can just approximate in this way, very trivially, very easily. Any question about this problem?
Well, I have other questions, but not for it.
Okay, so if no more question about this problem, now you can ask questions about the homework. This time, I mean homework 2. If you have more questions about homework 2, feel free to ask. Okay. I think you may have some careless mistake for the homework 2, or some very easy to change mistake. So just for this problem I mentioned, most of you didn't do it correctly, but other than these problems, I think most of you did quite well. But if you do have any other question, just feel free to ask. Okay.
Well, I have questions not with homework too, so I can just wait till till people ask their questions.
Okay. So any question about homework 2? Any question? Okay, if you have further questions, well, feel free to ask me in my office hour, 2.8. Oh, okay, 2.8. You have this function, which looks like this. And he wants you to verify that, well, the Fourier coefficient is equals to e to the INX over n. Okay, this is very easy to ask to verify, but you have to verify. Don't forget, you still need to do some integration by part and then try to check that. And well, he wants you to say that this kind of thing, it actually converge. Okay, it actually converge. And although this function is not continuous, so we cannot really say that these functions this Fourier coefficient, the Fourier series will converge to every point of this function. But we want you to show this sequence converge. Okay. Why this sequence is converge? I think a lot of you did very, very beautiful. Why this sequence converge? You can actually use a Dirichlet test. That on problem number, well, exercise number 7. Okay. It is of 2 parts. This sequence formed by 2 parts. This is, we can call it Bn, this is An. An tends to 0 monotonically. Bn, if you take the partial sum of Bn, is always bounded above. Okay. So for any x not equals to 0. For x equals to 0, yes, of course. For x equals to 0 is it's actually equals to 0, right? Because the positive part will cancel the negative part, so it will be 0. So if x not equals to 0, you have this this sequence will converge. Any other question? Any other question? For your homework? Or any other stuff? Any other stuff? Because it's still my office hour. It seems that I'm a little bit late for today's class, so I'll be here for 15 minutes more. Okay, I'll be here until 6:15. If you have any other questions, feel free to ask. Otherwise, feel free to go.
I have a question, actually a lot of questions. Give me a second. Oh, so in the exercise 20, I think that's from chapter 2. Like, where we have to solve the Dirichlet problem for the annulus. Like, I know that the step should be us trying to find u, fx, g, or fr, g, theta, and then we plug it in the Laplace equation, and then we basically get r squared f double prime plus r f prime divided by fr equals to minus g double prime divided by g. So like I got that part, but here we have to like decide which of them should be positive lambda, which of them should be negative lambda, right?
Yes, yes.
But my problem is that I don't know how to decide that.
So you mean you try to do the separation of variables, right? And then you have an ordinary differential equation. All right. So then you have to determine the coefficient whether it's positive or negative, right? So you can see that again. This is on the disk. It's periodic, right? So I think what you should get is again Cn of r, something like Cn of, well, let's say it's Cn of r dn of theta. Okay.
I think we haven't like how it should look like on the next page. Like
Where is it?
on the next page.
Yes, I think so. We should have Cn of r e to the in theta, right? Eventually, you can write it like this, or you can write everything just like this. Okay. And then you want to find the equation on Cn, right? But I think, well, this is still separation of variables, so you should write it as Cn of r dn of theta. And then plug in, and then try to find the differential equation on Cn and dn. And you know that dn of theta is periodic in theta, right? You can conclude that, okay, you have something on Cn, I think it's Cn r double prime minus n or minus r Cn of r divided by Cn of r, right? Is equals to dn double prime of theta divided by dn of theta is equals to lambda. I think this is what you have.
Yeah.
This is not really Cn dn because we don't really have n at this moment, right? You just do a separation of variable.
Yep.
There's no n. Then you know that, okay, d double prime of theta over d double prime of theta minus d theta equals to 0, right? A lambda, right? So d is periodic. So lambda must be a negative number.
Wait, why?
Because if lambda is positive, okay, if lambda is positive, then that means d of theta is equals to a e to the theta plus b e to the minus theta.
Oh, which
Of lambda, which is the solution of this ODE. I think we discussed this before.
Yeah. And it's not periodic because
It's not periodic.
Okay, sure. And so we decided that. Okay, I see. And then I actually had a question. So about the same thing. So when we get C double prime R minus R C prime minus lambda C equals to 0, it's the OD solution. Is it like some sinus or is it?
I think you already did that problems, right? You shown that the solution must be r to the power n, something r to the power n plus something r to the power minus n, right?
Wait, wasn't it another thing? I think it looks like
it's just this two, right? There's two parts. It's the same as before.
okay.
Same as before. Right? It's exactly the same as the problem you did before.
I think the problem we did before, it was f double prime divided by fr. Wait, what?
I think it should be the same as this because you have the same differential equation.
Okay.
You have exactly the same partial differential equation. This is the partial differential equation you have, right? You just change the boundary value. So you should have the same thing as here.
Wait, it's 11th exercise where?
Chapter 1.
Chapter 1?
Almost, yes.
You do it? Okay.
You did it, yeah.
Okay. I actually don't remember doing it. Well, okay.
We've done that before, yeah.
Okay, sure. Thanks. And I kind of think I did the number 2 in chapter 3, but the techniques there, like, I guess I right, but I don't understand why they are right.
You mean this one? This one? Well, you guys haven't learned this ODE, right? So which is why sometimes it becomes hard for you, so I will try to avoid that. But the very basic thing you have to know, for instance, well, what kind of, well, this kind of solution, what is a solution for this ODE, right? You have to know when lambda is positive, when lambda is negative, what is the solution of this? You must know this. And you must know what is f prime equals to lambda f, what is the solution to this ODE, okay? Other than that, I don't really ask you, and well, I may assume you don't know, and I'll assume you may have some time, you may need some time to solve it. But for this too, you have to know what is the solution of that, okay?
And in chapter 3, exercise 2, like so basically
this is not an easy problem.
Yeah, I kind of did it in the sense of like I took partial sums, kind of like so. Yeah, and so I showed that they're a Cauchy sequence. I think
yes, that's good. Yeah.
Yes. And then basically because it is a Cauchy sequence, it's converged to a limit. I call it B, and so that's basically true. I get that partial sums they converge to some partial kind of B, and after that, okay.
But last step is not very easy. You have to show B is in L2, is in little L2.
Yep. And so I was kind of trying to do that using okay, so basically after that okay, with that sequence okay, and so basically I was trying to show that if we take wait, what did I do here? Huh? Oh, okay, I see. So I was trying to say, can I say this, like if the partial A minus partial B, like you know, we have a sequence of A, so when K goes to the infinity, I'm trying to argue that like the difference between AK and partial B, it goes to 0, and I think I proved it. And then can we say if the partial sums are from minus n to n, so it has like a boundary, and can we argue if we proved it for like all finite n's, then for like when n goes to infinity, it still would hold?
You mean, well, I think you cannot really do that, right? You see, this is actually like a double limit. So you have to be very careful when you try to deal with double limit. You have this, the summation A and K minus B K, where K from 1 to capital K, right? Square. And if you have this, I think you have this n goes to infinity, it will tend to 0. Right?
Yeah. And then if we
tends to 0,
go into infinity, would it still go?
Well, you have to do that by the definition, and then you will see why it may not be true, okay? You see, this means if you take the limit as n goes to infinity, 1 to k, a n k minus b k squared is equals to 0, okay? Then if you take the limit in k, of course, this is a number, so it's 0. That's true. But now what you're trying to do is you try to switch these two limits. You try to change the order of these two limits. Then it may not be true. Okay? This may be true.
Then I have no idea how you can approach that question then, because I don't know.
To be fair, I don't really want to give you any further hint for this one. Try to think about it, because this is a very interesting problem. Okay, try to think about it.
Okay.
If you are not able to finish it, it's totally fine. Yeah, because this problem is it's a very typical analysis problem or mathematical analysis problem. Try to think about it.
Okay. Oh, okay. For this one, I maybe know how to do it. Okay. By the way, that's something unrelated to class, but did you see that we have to register for classes?
Yeah, you have to make a schedule with me. Yeah, that's true.
Yo, what time do you want to meet?
Maybe after this midterm.
Okay, because I actually looked at classes and I don't think I have a lot of choice there. Basically, I just have to take 4 math classes.
Okay. So do we have any math class next semester?
No, actually, we do have quite a nice amount. We have complex variables and advanced linear algebra, and we have numerical analysis, and we have mass modeling. And
I see. That's nice. That's nice. Yeah. I think other than complex analysis, all the other courses are more applied, but all of them apply math courses. Yeah, it's very nice. Complex analysis is slightly different. Who will teach complex analysis?
I don't know. Oh, I think it's a new professor.
I see. No, that's nice. Yeah, that's pretty nice. Well, you will see why complex analysis is very interesting. But well, anyway, yeah. We can make schedule like on Friday, maybe. Yeah.
Okay.
Well, just send me email. When do you want to meet on Friday? Then we can meet. Okay.
Okay. Okay. Sounds good. See you later.
Okay. See you.
Hi, Professor.
Mm-hmm.
I think I have some problems.
Okay. What's that?
I think I have a lot of them, so maybe I can just ask several of them today and like postpone.
Okay. No problem.
So please feel free to tell me if you have to go. All right.
Okay. Yeah, I don't have anything to do today, so it's fine.
咦，我们是不是可以说中文了？好久以前
好，可以，你说吧。
我发现我完全跟课程落在了整整1个周。
哪有啊？为什么呀？我觉得你这个你听着非常的明白，我觉得。
这 homework 是周天才交的嘛，然后我上个周，所以
你说上周这个是吧？好吧，你说吧。
今天的确实听得还不错。
对呀，这个我觉得也不是很难，而且你今天听得不错，那上周也听得不错，上周就是在讲那个今天的这个东西啊，对不对？
不是，但是上周周四的 lecture 我当时翘掉了。
我知道，但是那个东西也没有特别关键的东西。那周四那个我不是讲的特别慢吗？那个当时我不是非常慢的，只讲了1个证明吧？我只讲了1个证明。
我只听了前半。
特别重要。
我还没有去 review 后半节。
对，但是那个证明也不是特别重要，所以这个基本上你也没有耽误什么呀。
行，那我今天回去再把 lecture 瞅一遍。
你可以看一遍，那个我记得我讲的还挺慢的，那个我就是因为你们都觉得这个太快了，所以我就弄的还是慢了一点。而且这个 proof 的话也不算很难吧，就是算起来稍微麻烦一点点。
好的。那我回去瞅一下。哦，对了，今天学的是不是也要考？
今天学的不考，今天学的这个东西也没办法考，这个东西，这个没什么考的必要。
好的，就是书上33页。
33页。
对。就是上面第一段有一个 measure zero， 我不知道它是什么意思哦。
这个你们现在不知道，这个你们不需要知道，你们这个 measure 这个东西的话，这个东西。你们要等到那个 real 就是那个实分析才要学。
行。
所以这个东西非常的，就相当于若干个点吧，你就可以认为它就是若干个点。
就是它就是我记得好像上课都说过，就一个函数，如果它是连续的，然后它是可积分，如果你只改变上面1个点的话，它
对。
一样。
就是这个意思，就是相当于你只改变了若干个点，好吧？就是这些点它的总长度是0。
哦，
你可以这样理解。
然后因为黎曼积分它取的是一个 interval 上面的 supreme 或者是 minimum 相同的时候，
对，
可及，所以说它不影响，是吗？
对，它不影响，可以这样去理解，可以这样去理解。
我觉得我还是就是那些什么就各种什么 convergent， 还有什么 interval， 就
这个东西我不是都已经说了吗？这个你们只要这个对着葫芦画瓢就行了。这个反正我也不要求你们真的知道太多。epsilon delta 这种东西肯定要知道，对吧？然后 uniform convergent 这种东西你们也得知道，对吧？然后就差不多了。
我再顺便问一句，那是不是我不知道我理解对不对？是 convergent 是可以推出 absolutely convergent， 然后
不能，这个不能的，就是 absolute convergence 可以推出 convergent，
对反了。
uniform convergent 是相当于是关于函数的。
那 uniformly convergent 它和 convergent 还有 absolute convergent 来比哪个更强？
你要知道这个 convergent 跟 absolute convergent 它都可以说成是它都是数的关系，就是数列的关系。数列的话，你求和对吧？看这个东西是不是 convergent， 或者是它的绝对值是不是 convergent。这是 convergent 跟 absolute convergent。Uniform convergent 是什么呢？是你有一系列函数，对吧？这一系列函数它是不是作为一个函数加起来之后是不是一个 convergent？
好，
不是把这一个函数每一个点就是 pointwise convergent， 不是把它每一个点看成不同的点，然后看它是不是 convergent， 而是作为一个函数整体看它是不是 convergent。这个是可以理解成为 uniform convergent。
那怎么看它是不是 convergent？
就是那个，就是我们之前说的嘛，就是 uniform convergent 是什么呀？现在我们只学过一种方法去判断这个东西是不是 uniform convergent， 或者用定义，对吧？或者就是你有一系列 f(n(x)， 你看这个东西是不是 uniform convergent 呢？你就看这个东西它的这个绝对值是不是小于等于一个 convergent 的一个 sequence， 这是数。这跟 x 无关。如果这一系列的函数，这个函数列，这每一个函数都比你某一个数要小，同时呢，这个 Bn 是 convergent， 对吧？那么我就可以推出来这个东西，这个函数列就是 uniform convergent。
这个定义我知道，但是就前面那个 f(n(x) 的绝对值，这个怎么看它是不是小于一个数？
那你看这一般情况下当然很难看了，对不对？我们比方说傅立叶级数嘛，这是傅立叶系数，就是傅立叶分析，这个就是一个最好的一个例子。你比方说是一个 e 的 inx 乘上一个什么 an， 对吧？那这个东西的话，那你要看它是不是比某一个东西要小，那不是太容易看了，对吧 ？e 的 inx 这种东西乘个 an， 你取个绝对值，对吧？那不就是一定是等于一个 an 的绝对值？这东西的 norm， 这东西的模长不是1吗？
是把它换成 cos theta 和 sin theta 之后。
对啊，这不是 cosine theta 加上 I sin theta。这东西的 norm 不是就是 cosine 平方加上 I sin 加上 sin 平方再求个根号等于1吗？所以这块都是虚的，就是某种意义上讲它是虚的。那所以这就是说，你这种东西如果足够好的话，你的傅立叶系数如果足够好的话，那它就整个就足够好，它就已经是 uniform convergent。
对吧？那比如说 cosine x 这个函数，它可以算是 uniformly convergent 吗？
你说这个 cosine nx 这个东西？
不，我就直接 cosine
x。cosine x 它只有一个函数，那你其他的函数是0 0 0 0是吧？那这是 n 个函数。
n 个。
对，你求和之后，你才能说它是不是 uniform convergent， 或者说你这个函数它有一个下标 n， 这个我们就管它叫做 capital Fn。如果这一系列函数都是 cosine x 的话，那 capital Fn 当 n 趋向于无穷的时候，那是趋向于 cosine x uniform， 对吧？n 趋向于无穷的时候。 因为这两个一减的话，它就是0 ，uniformly 等于0，对吧？所以这个肯定没问题。就是你要知道，就是数列的收敛跟函数的收敛这是两个东西，因为函数它里面有好多变量，对吧？所以收敛的时候就要涉及到这个，你这个收敛是每一个点固定下来是收敛的呢，还是你有更好的收敛性质？数列就不一样，数列就是只要收敛它就收敛，对吧？
然后是如果它是 uniformly convergent， 它一定是 pointwise convergent。
对，如果是 uniform convergent， 它就是比 pointwise convergence 更好。不仅有这个收敛之后的，比方说它的极限是 f， 对吧？不仅有这个每一点都等，对吧？而且你求导之后，它还是每一点都等；求积分之后，它每一点还都是都等。
好的，我通透了一些。
好。
然后38页，38页就是那个 equation 1下面那个。就是 equation 1下面那个，就是有一句第二行是 integrable function at one point without changing its Fourier coefficient，就是刚才那个是一样的。
对，刚刚那个是一个意思，就是你改变一个点跟你积分没有关系。
好的。然后41页 Corey 3，这个我写的是啥？这个我会再瞅一眼。
好吧，这个就是我们刚刚说的这个东西嘛，就是我们说的这个东西嘛，对吧
？Corollary 2.3吗？
对啊，这个不就是这个东西吗？
对，
这个说的就是我们这个东西，对吧？
好的。
因为它就是 uniform convergent。
然后就是43页中间那个 equation， 就是最右半部分是就 integral， 然后绝对值小于等于 c， 这是因为 f 两撇 x 它是 integrable， 然后所以说它就是 bounded， 是吗？
对，它应该是，它其实是连续的吧 ？f 两撇 c，f 两撇 theta 是一个连续函数，对吧？它不是说这个 twice continuously differentiable， 也就是说这个二阶导数连续的。
二阶导数是连续的。
对，二阶导数是连续的。它连续的话，那就是在一个 B 区间上是有界的。
等一下，我有哪些函数它是有界的？
不是。首先，连续函数在 B 区间上是有界的。
这个好像368即将学到，但是还未学。
这个你们101就学过，好不好？是啊，你们101就讲过了。这个你都好吧，无所谓，反正这个你是这个需要知道的，好吧？
好的。
连续函数在有限，就是在 B 区间上是有界的。然后还有是那个可积函数是有界的，黎曼可积函数是有界的。
那这个黎曼可积它就不一定是有界的区间了，是吧？
你要这么说的话，一般情况下我们都还是说有界区间。如果是无界区间的话，它就是奇异积分了，对吧？就是 singular integral。singular integral 那样说的话不太合适。我们还是假设有界区间嘛，就是你在一般情况下都是可积的那个区间，它是有界的，只要是正常的积分。
好的。然后好，这个我明白了。44页，是44页。44页，一个是那个 average value 的意思，我有点迷惑。
就是你可以看嘛，那个 average value 是在哪儿提到的？
左边中间那一段，第三行左边。
左边中间那段。
再往下一段。
对，你看啊，就是其实你把这个 G 给它看成是某一个权重，好吧？这个是什么呢？这就是你 f(x) 本来是 f(x)， 现在呢是你 f(x) 稍微移了一点儿，然后乘上这个，加上移了又往右移一点，又乘上这个，对吧？就是你来回移，你这个 f(x) 减 y， 对吧？你这个 f 本来我是想看它的 f(x) 的值的，你就这么想，本来我想看的是 f(x) 的值， 现在呢，我把这个 f(x) 给它做了一个变换，就是乱移了一下，然后乘上了一个 g， 然后做了个积分，对吧？
嗯
那我就可以把它给看成是本来是 f(x)， 然后把 f(x) 稍微移了一点儿，乘了个 g， 然后做了一个积分，对吧？这说明是你作为 g 作为一个 weight 作为一个权重做了一个平均
啊，
附近的值做了个平均，
有点不能理解，是啥意思？
就相当于你把 g 啊作为一个权重，你比方说你看啊，比方说我这个东西，这个 f 在这几个点上有定义，对吧？
嗯
我想看这一点上的值，这是 f， 对吧？
嗯，
那我干了一件什么事儿呢？比方说，我 g 在这一点上，g 在这个点上，比方说是，反正它就是我们就先看这一点吧，就是我想看这个 f 在，比方说这是1，好吧？我想看 f 在1这点的值，这本身是 f 在1这点的值，没有什么问题，对吧？
嗯。
但是现在呢，我关于这5个点，我做了一个加权平均。我不这么做，不看这个1这点的值，我看什么呢 ？f1 减0，也就还是1这点的值，乘上了一个 g of 0，对吧？
嗯
然后再加上了一个 f1减1 g of 1，好吧？然后这是0，好吧？这是负1，这是2，这是3，比方说。然后我又加上了一个 f1减2 g of 2，好吧？然后加上了一个 f1减去负1 g of 负1，对吧？然后我又加上了一个 f1减掉一个负2 g of 负2，这是1、2、3、4、5个数，出了个5，我们做了一个加权平均，对吧？
哦哦，
这是看本来我看的是这一个点，现在我是看这个点跟它周围的点做了一个加权平均。
嗯哼，
那加权平均，如果你把它连续化了之后是什么呢？加权平均实际上就是一个积分再除以这个区间长嘛。
嗯，那也就是说，jx 这个函数代表 f(x) 这个点上的权重吗？
就是 f(x 减 y) 这点上的权重。
然后 jy 是代表它 f(x 减 y)
就是一个权重，你可以看这样看，但因为它是对称的，所以你也可以反过来看，对吧？这两个都可以。但是你如果对于我们具体的问题的话呢，一般情况下 g 是一个显示，就是比方说我们的digit kernel， 对吧？那么你可以把它看成是你关于这个 digit kernel 或者是关于一个 good kernel 做了一个加权平均，对吧？就是这样的一个 good kernel， 就这样一种 kernel。你做了一个加权平均，这个加权平均是什么意思呢？就是说，当这个 y 等于0的时候，就是当 y 等于0 g 0的时候特别大，其他地方呢比较小，这几个比较小，对吧？这样做加权平均的时候 ，y 等于0的时候特别大，这项特别大，就是突出这一项，其他东西呢比较小，但是能够呢让它变得光滑一点。这个多少跟它周围的数做了个平均，对吧？那跟它周围的数做个平均之后，它跟周围的差应该就变小，对吧？就这么想。
行，我回的。好的。然后就紧接着那个下面就是那个 SNFX， 就44页。
我看一下。
最下面那个 SNFX 那个是倒数2、3行，我不是很懂他是怎么把 EINX 打进去的。
这不就直接拿进去吗 ？e 的 INX 乘上这个 e 的负的 INY 嘛，这里面是积分，这里面是关于 y 的积分，对吧？
对啊。
那所以这是个常数。
啊？哦，
这个在里面看的话是个常数，对吧？
等一下，哪个在哪里是个常数？
e 的 inx
啊，
关于 y 是个常数，
哦，
对吧？
是哦，哦，是这
所以
样。
你可以把它拿进去嘛，就是你把它拿到这个积分式子里面。
哦，是这个样子。
对，
好的，
嗯
好的，明白了。
嗯，
谢谢教授。然后6页，
嗯，
那46页上面那个最上面那个